Yeah. So we are aware of all these ChatGPT and several other dialogue systems, and they're quite popular these days. So what we do today is we look at some recent uh, deep learning based approaches for developing these dialogue systems. So dialogue system research has been started long back, and people have developed rule-based approaches, then template-based approaches to develop dialogue systems, conversational agents. And we will mostly look at, okay, what deep learning approach is there, and also in general, the framework of dialogue systems, what framework do they generally follow in order to accurately produce some conversations. Yeah, so this is something you all know. It's very, very useful in real life in several businesses, several applications started using these conversational agents or dialogue systems. It's quite popular and its market size is quite large. Most of these dialogue systems are currently based upon deep learning techniques. Earlier, people used uh, these rule-based techniques and template-based techniques. So we will look at these deep learning based techniques in specific. Okay, generally, whatever deep learning techniques that we have studied, what all deep learning techniques have you studied in the NLP course?
RNN, LSTM, then transformer.
Transformer,
Yeah.
RNN, LSTM, and so if you look at those models that people generally use in NLP, they follow a specific uh, architecture, right?
Yeah.
And something like encoder decoder models. You aware of encoder decoder models?
Yes.
Yes. Yes.
Yes.
Yeah. So they follow some sort of an encoder decoder models in most of the for solving most of the NLP applications, and that those kind of models, all those deep learning models that you have studied, encoder decoder models based upon RNNs and STMs or based upon transformers, everything can be useful for modeling the dialogue systems also. And apart from that, dialogue systems may have some specific aspects that requires you to come up with some techniques specific to dialogue systems. And we look at a couple of such deep learning models also. And in general, the dialogue systems can be classified into two types. They are the task-oriented dialogue systems and open domain dialogue systems. And we will look at these categorization of the dialogue system in slightly into detail. So a general categorization of the dialogue systems is
Sir,
task-oriented. Yeah.
sir, can you please, minimize this window? It is coming up.
I
Slide
see, I
is
see.
not.
Yeah, yeah.
Thank you.
No, it's fine. Yeah. So a general categorization is task-oriented dialogue systems and open domain dialogue systems. So the task-oriented dialogue system aims to solve some specific problem in some specific domain. Okay, one typical example is, okay, you want your conversational agent to book a movie ticket or book a restaurant, reserve a table in the restaurant. Now you want your conversational agent to take that specific actions, okay, or solve some specific task where you want to use it for booking tickets for movies or reserving tables in a restaurant or right. So these can be considered under these task-oriented dialogue systems, while open domain dialogue systems are generally you use to chit chat. So on some specific domain or or anything, okay, nothing specific to any particular domain, but in general you want to chit chat with these open with these conversational agents, which can be classified as open domain dialogue systems. In either cases, the fundamental, uh, from a machine learning perspective, fundamental idea is that you will be having some uh, user messages in the form of something like you. So you is a user message, right? Which consists of some sequence of words, something like you want you to up to UI, and then Based upon this user message, this conversational agent has to produce some response, which consists of some sequence of words. Okay. So fundamentally, on all these conversational agents, irrespective of whether there is open domain or task oriented, the idea is to produce this response based upon this user message. Okay. So you want to learn a function file, okay, function file, which maps you to R. And in generating the response, often these systems also have to make use of some external knowledge base. So this file is often going to be a function of both the user input and some knowledge base it queries, which is represented as K. So this is a typical, system how it should behave based upon this user message and based upon whatever information stored in the knowledge base, it has to produce some response R. Okay. So here in this table, there are some examples of task-oriented and open domain dialog system. Okay, here's an example of a task-oriented one. So I need to find a nice restaurant in Madrid that serves expensive Thai food. So in this case, the conversation agent has to find out some specific particular restaurants, have to solve some particular task, right? And it makes use of some external knowledge base, something called the restaurant database, to find out some specific uh, restaurant which satisfies these constraints. And then it has to generate this answer in the form of a sentence. It says that, okay, there is a restaurant called Bangkok City, located at 900 or something like that. So it has to generate these answers in a natural language, and it has to understand the user message, and based upon that, it has to query the external knowledge base and get some answer, and based upon that, it has to generate some response in a natural language. So this is fundamentally what it has to do, and in order to achieve this, it, it follows a specific architecture, and we will come to that soon in a later slide. And here you have some example of open domain dialog systems where somebody is just talking about some things like biological visualness. So it answers like it's a famous Chinese dish, etc., where it is not required to take any specific actions. Okay, I think fine so far, right? Yeah. So when it comes to task-oriented dialog systems, as we see, it has to solve some specific task. It has to find out the intent of the user, what the user is asking about, and about on which domain. This is all about the restaurant domain, right? Or food domain. So, it has to identify which domain the user is talking about so that it can query appropriate database. What's the intent of the user? What the user is asking about a restaurant or a location or a food, etc. So that intent of the user also has to be identified. On the basis of all these, it can query an appropriate database and get an answer. And then it has to generate these answers back to the, this answer it has put in the form of a natural language back to the user. So in order to achieve these things in a very accurate manner, the task-oriented dialog systems follows a modular structure, a pipeline structure, where it solves one task, one after the other. Like the task, the solution to a final generation of this output consists of solving multiple tasks in a sequential manner. It follows a pipeline structure. And generally, it's some structure that people have been following in last decade or so, but recently people have came out of this specific pipeline structure and they are trying to solve everything end to end using a deep learning model. Just provide this as input and generate this as output using a deep learning model. Somehow trying to bring this knowledge bases also into the part of the deep learning architecture. So there is a end-to-end learning that people have been following in recent times. But in general, you can think of task-oriented dialogue systems to consist of four modules. One is natural language understanding, which is understanding the user message. Then dialogue state tracking. So now all these different modules we'll be discussing in detail in the later slides. But in an abstract manner, the idea is that okay, to understand the intent of the user, if it is about some domain like restaurant, then the user might be asking about the kind of food, the kind of location where it has to be, and some other things like if the restaurant is costly or cheap. So trying to identify all these different intents of the user, and keep track of that based upon the conversation with the user is that part. That's what this dialogue state tracking module does. So now after few conversation with the user, you'll be the system, the agent will be having complete information about all the things that the user is requiring with respect to a restaurant booking. And once it has all the required information, then now it makes an action. The action could be querying an appropriate database and get some restaurant name. It has to perform some action. And what action to be performed is determined by this module, which is known as policy learning. And once on the base of action, it receives some answer, and to present that answer back to the user in a natural language, there is some component called natural language generation module. So these are the different modules which is present in a task-oriented dialogue system, which we will be looking at later. And when it comes to open domain dialogue systems, uh, they are generally, the three types of open domain dialogue systems. One is generative systems. Generative systems does an end-to-end generation of the dialogues. Okay? It uses some deep learning models, such as sequence-to-sequence models, encoder-decoder models, to map the user message and the dialogue history into a response sequence. Okay? There is nothing intermediate step, or there is no uh, structuring of the entire process into different pipeline or modules. It is just end-to-end generation based upon deep learning. And then there are retrieval-based systems. So the retrieval-based systems generally maintains it's kind of a system that is used earlier before the advances made in deep learning, where people maintain some uh, template, some containing the set of responses to be produced. And the retrieval-based system has to rank all those responses in that template and provide the highest ranked response as output. So then there is this mix of both these approaches, which is generally known as ensemble methods. Okay, so far everything is fine, right? With respect to these different modules of the task-oriented dialogue system, we will look it into more detail in a later slide. I hope there is no issues with audio. Yeah.
Yes, sir. I have one query on the earlier slide, uh,
Sure.
where we are saying that external knowledge is also an input. So does that mean like if we consider the user messages as some prompts, then it will include the input will be user message plus external knowledge reference like that?
Hi, so if we are looking at an end-to-end system where you need to generate the response using a deep learning model, you can think of this user message as a prompt plus some additional information that you have retrieved from the external knowledge base and provide both these to produce some output.
Okay.
Yeah, so as I already mentioned, if you look at this dialog system uh, area, maybe at least 10, 15 years back, it was majorly based upon role-based techniques. And uh, it is based upon some machine learning techniques are used, but not neural network-based techniques, but machine learning techniques. And the idea behind the role-based technique and most of the machine learning techniques is majorly that you will be some template will be there. You need to choose some particular template depending upon the, the user message, and then you need to fill the slots in that template using some machine learning approaches. And the slot filling can be seen as some kind of a multi-class classification where using a machine learning technique, you can fill the slot. So these kind of techniques are often very restrictive. They have to be fine-tuned to some specific domain, specific tasks, and they cannot deal with situations which are outside the situation where they have been trained on. But no, uh, with the advances in deep learning, people started using deep learning models which is capable to generalize to a lot of unseen situations. And the current state of the data systems are all based upon deep learning. So when it comes to deep learning models, as in most of the NLP, natural language processing problems, one uses sequence-to-sequence models of encoder-decoder kind of models in solving these dialogue systems also. But dialogue systems also require some performing some classification as well, where one uses some deep learning classification models as well. So we will uh, labeling sequence to sequence models will be useful. But when it comes to dialogue system,
Sorry, sir, I can't hear you. I don't know if it's a
Yeah,
problem on my side, but
no, we
Yeah,
lost his voice.
it's
Same for me.
same. Yeah.
So, sir, we can't hear you. I think we should be messaging to sir. Let's see.
hello.
Sir, we can hear you now.
I'm sorry, got disconnected. Uh, yeah, so this is slides are visible, right?
No, sir, slides are not visible.
I think it should be visible, isn't it?
Sir, your screen is now visible, but we see the teams on your screen now. Yeah, we
Yeah,
can
and
see.
now you can see, right? Yeah, but when it comes to dialogue systems, there are some specific use cases in dialogue systems for which one may have to develop some specific kind of deep learning models. Okay? We will see some examples where one may have to develop some specific deep learning models which can copy the input as it is to the output. Okay, so there will be situations where user will provide some message, and this agent has to produce a response which is very similar or which contains the same words as the user has provided as input. Right? It doesn't have to generate any other words in the vocabulary, but only some specific words which is provided as input in the user message. So that kind of systems, okay, requires you to just copy what is there in the input to the output. And the people have developed some deep learning architecture specifically for these kind of situations, and they are needed for dialogue systems such as PointNet, CopyNet, etc. And another aspect is that many times you want your deep learning models to take into account the content in the knowledge bases, information in the knowledge bases, and they have to combine the user input with knowledge base in order to produce the output. And specific kind of deep learning models have been developed for this purpose also. So we just start looking at a couple of such deep learning models just specifically developed for dialogue systems. Okay. So one such model is, or one of the very early models in this deep learning and dialogue systems is something called the hierarchical recurrent encoder decoder. So we are already aware of this encoder decoder models. So in the case of encoder decoder models, you say, for example, if you wanted to do summarization, machine translation, question answering, there will be a input sentence and you want to produce some output sentence, right? In dialogue systems also, it is something similar. There will be an input sentence, which is user message, and the agent has to produce some response, which is again a textual response. So the standard encoder decoder models can be used in this situation. But when we use the standard encoder decoder models, where we consider the user message as the input, and then you aim to produce the system response as the output, then it does not keep track of what the user has discussed in the past. It is just based upon the current user message you are trying to produce an output, right? But many times the output that you have to generate will depend upon what you had discussed previously with the user. Okay? Whatever user messages which is there in the history. Okay? And it has to produce an output based upon not only just based upon the current user input, user message, but also keeping track of the history of the user messages, or keeping track of the uh, you know, context in which the whole dialogue is happening. So some additional work has to be done in order to maintain or in order to take into account the whole context associated with these dialogue systems. And some researchers came up with this hierarchical recurrent encoder decoder model. So if you look at this architecture, so this is the architecture of the hierarchical recurrent encoder-decoder model. And if you look at this architecture, so you can see that there is this standard encoder-decoder here. So this is the these two components are nothing but the standard encoder-decoder. So what this encoder is doing, the encoder is considering this user message. So there's a user message, something called what is wrong, and some agent or somebody have to generate an output message and like I feel like I'm going to pass it. So it can be done just by considering. So this generation of this output can be done just by considering this input alone without considering any dependence with the past, and one can just use a encoder like this, which maps this input message into some hidden representation, and then that was using this output. But in dialog system, no one had to keep track of whatever has happened in the past. Okay? So the different user messages and its response are often in dialog systems called turns, different turns. Users and agents takes turns in answering, and you want to maintain some kind of a dependence with previous turns also, and one have to maintain some kind of a turn level representations also in the whole system, that the learning models that you have developed. So you need to produce this output not only just based upon this given input, but also somehow you take into account the dependence with the previous user input and output, and basically by taking into account some kind of dependence with the hidden representation associated with the previous user input and output. So so there has to be some modification that has to be made in the standard encoder decoder framework in order to capture that dependence with previous turns, okay? The dependence with the previous turns. And what they have proposed is that, okay, we can capture that dependence with the previous turns using a RLM. It maintains a encoder to map this current input message from the user into some hidden representation. So then there is another recurrent neural network here. And this recurrent neural network is keeping track of the dependence across different turns. Okay? So this hidden state is something associated with the previous turn, and there is a hidden state associated with the turn before that, etc. So that dependence with the previous hidden state is made using this recurrent neural network. And what this recurrent neural network does is that it considers the hidden state of the previous turn as one of the input, and the hidden state that you have obtained based on the current input message as another input. So that is a typical RNN model. The typical RNN model is of this form, right? And this is the repeater. So what this RNN considers as hidden representation is from the previous stage is the hidden representation of the previous turn. So this hi minus 1 is the hidden representation associated with the previous turn. So this input xi is nothing but some kind of hidden representation that you have formed out of the current input message. The hidden representation that you have formed out of the current input message is passed as input, and the hidden representation from the previous turn is as the previous hidden state. The hidden representation in the previous message. And based upon that, combining these two aspects, it tries to generate these output sentence using a decoder model, which is again a RNN. This is the standard decoder, which considers this hidden, which tries to generate this output based upon this hidden state, which is a kind of representation of both the turn level representation as well as message level representation. Is this architecture clear?
Sir, how this is trained on the same like dialogue kind of database?
It is trained on the same dialog databases in an end-to-end manner.
Okay, and it doesn't have any
so
knowledge
this
base.
is mostly for this is mostly for open domain dialog systems. You just want to have some kind of a chat code which can just chit chat with the user.
Okay, sir, thank you.
Sir, but yes, sir, will go ahead.
Okay. Yeah. Sir, in this, the right part is token level RNN, right? And the left vertical part is turn level context.
Yeah.
Is that right, sir?
You mean bottom?
So in this architecture, the right part,
No, there is no. Okay, it's not. It is not like divided into right and left. It is divided into. Okay. Okay.
Okay.
So there is one
bottom and up layer, is it?
RNN here. Yeah. So this is this. Okay. This is the RNN which considers some input and dependence with the previous state. So this RNN can be seen as a at a higher level, captures the dependencies across different turns. Each turn can be seen as a combination and corresponding system response. And there will be sequence of some user messages and system responses, right? So this is a RNN at a higher level, which captures the dependence between different turns. Okay? The dialog state or in the dialog systems. And to this RNN that you have, you need to provide some input, right? So what are you going to provide this as input to this RNN? The input to this RNN is nothing but some representation of user message associated with some particular term. Okay? So this is this turn, this particular turn, the user says in the voice, and we to generate some response that I feel like I am going to pass out, or the vice versa. Maybe the you know this is the system at a particular term. This is one particular term, and to this RNN that you have, you pass as input an encoding of this user message. So the encoding of the user message is done using another RNN, an encoder RNN. So what we have here is the encoder RNN, which encodes the user message to get some hidden representation, which is a hidden representation corresponding to this particular user message. Now that hidden representation is provided as input to this RNN, which is the RNN at a higher level, or known as a hierarchical RNN. And this RNN computes a hidden representation based upon this input that you have passed to this input that you have obtained from this user message, and also the hidden representation from the previous term. Using the hidden representation from the previous term in order to capture the dependencies of the previous terms, and which is obtained from the current user input is encoder RNN. It tries to form some hidden representation associated with the current term. Representation associated with the current term is used by this decoder RNN to generate this response.
Sir, your voice is breaking. I mean,
Okay, but is this clear?
So,
I
so sir,
mean,
this part which you written, sir, encoded RNN, hierarchical RNN, decoder RNN, this forms the token level part of the architecture, right?
See, only this forms the token level architecture. Only this is
Okay, only the
token
bottom
level.
part, only the encoder
Encoder
RNN part.
RNN. That
Okay.
forms the token level.
And similarly on the left side, whatever is the bottom part, that is the turn level.
This is token level. This is token level. This is considering a particular message and trying to find out a embedding associated with that message. So this is again a encoder RNN,
Yeah,
which
because
provides a token level representation. And
yeah.
this is the RNN, hierarchical RNN, which tries to find out a turn level representation.
Okay, so only the bottom, only the middle layer of RNN, that is the turn level context RNN, and
Right.
other parts of the architecture forms components of the token level RNN.
Right. So this is the
Okay,
token
got it.
level RNN, which tries to encode your message to get some representation of the message. And this is the hierarchical RNN, which forms some turn level representation by taking into account the dependencies with the previous turns. And then this is the decoder. So this one is the decoder RNN that tries to produce the message based upon this encoding that you have here, which considers the dependence with the previous turns as well as the current message.
And how does these two decoder layers are interacting, sir, or they are independent? Two decoder layers, one at the left, one at the right.
These
They are same enrolled
two
in time.
decoders make
Okay,
use of this representation that you have.
okay, sir, got it. Yeah, thanks.
So the hierarchical RNN representation, they make use of that representation of the hierarchical RNN, which mainly is that turn level representation. And they use these to generate your system response.
So how long history it can track? Can we even control that parameter?
See, so whatever they propose the standard are so it may not be tracking very long term. Is perhaps we can replace with the LSTM or so which might be able to capture slightly more long term. But I don't think you may need something beyond 10 or so. I'm not sure.
Okay.
Sir, one question.
But
One question. Uh, till like, I mean, will it always be continuously generating the output? What is the stopping criteria?
So this is like generating the output for some specific user response, right? So whenever there is a user, not a user response, but when there is a user input, it has to generate a response. So it will stop when there is no user response or user says, okay, bye, thank you, or something like that.
So in this particular example, I believe the first sentence is a user input, right? And the
Yeah, I'm not
intermediate.
very sure about how what. No, okay, don't really look it into what these examples would be. But this is the general architecture where you have here the user input, the response, and then you have another user input here and the system response here.
I believe this system response from the first decoder instance is fed back into the system, right?
I forgot about it. What exactly is happening here? You can just think of this architecture as considering some user input and generating some system response, and then for the next user input, generating the system response.
Sir, one question.
Yes.
Sir, in case when there is some random conversation, for example, if user has given 2, 3 inputs which are very random in nature, these are not connected, then in those cases, do we need this hierarchical connection?
Well, it might not be required, but perhaps your model might also end up learning that, okay, no, there is not much dependence with the previous hidden representations, therefore the weight that connects the current hidden representation to the previous hidden representation also would be low.
So
Yeah,
during
but if you
training
think that,
itself, we
okay,
need.
every user input is not related to the previous user input, you may not need a hierarchical model, but a simple encoder decoder model is sufficient.
Sir, in this example, first input is I don't feel so good. What's the next user input here?
Uh, I don't know, like I don't know what exactly is with respect to this example, but forget about what is happening with respect to example. In general, you can think of this model as responding to some particular user input, whatever it is.
Okay, sir, got it.
Sir, I believe this is mainly to showcase the training part of it, wherein it is just trying to understand sentence by sentence and generating the subsequent sentences. While at the inference level, I believe whatever you mentioned should work just with one user input. It will just generate the next input. Yeah.
I see, that makes sense. Yeah. As far as training is concerned, yes, you can do that. Okay, so this model is clear, right?
Yes, sir.
Yeah. So what it basically tells you is that, okay, you need to maintain a higher level RNN which keeps track of the different history of user input and system response. So that keeping track of the history is helpful in generating an accurate system response. Yeah, so now, so we look at some other models which are specifically needed for these dialogue systems. Many times in many applications of dialogue systems, there could be situations like the user provides some input like, okay, hello, my name is Rich, and the system just has to generate answers. So all it does is that it is generating some words which is already there in the input. Okay, so this is unlike the standard generation process where you may want to generate some completely new sentence. You don't have to do it. You just put it some parts of the input message as the output. So if one uses the standard encoder decoder methods, it might need just copy what is there in the input as the output. And many times it fails to just do this copying of the input to output. So people have come up with some ways to overcome this and come up with some kind of models which can simply copy the input to output. So we'll see how they done. Okay, if you so first let's look at how the standard the encoder decoder was. If you bring this attention, we can do this encoder decoder model. In the standard encoder decoder models, many of these models make use of this attention mechanism to improve the predictions, get an accurate generation of the output. So this is how they do it, right? So if you have some kind of a input, which is x1, x2, x3 up to some xt, right? Using this encoder, you form some kind of a hidden representation and let this represent those hidden representation. Okay? In this example, they may be using some bidirectional LSTM or bidirectional RNN, but you use some encoder model or transformer model or anything. Okay, when it comes to transformer, it's a completely different mechanism. But let us assume these LSTM-based encoder decoder models where you form these hidden representations for each of these elements of the input. And now, what happens at the encoder level? So when you want to predict the output YT at some time t or some turn t, what you do is that you consider these all these hidden representation associated with the input and consider some kind of a weighted combination of that. Something like j equal to 1 to t alpha ij hj. Okay. So what you're trying to do is that you're trying to predict for the ith term or the ith step at the decoder level. And when you're trying to predict for the ith step of the decoder level or any step of the decoder level, you try to consider some kind of a weighted combination of the hidden representations as with the input. And these weights will be different for different steps of the decoder. Okay? For the first stage or the first step of the decoder, it uses some different attention weights. Maybe it gives more weightage to the first input. Maybe at the last stage or the last step of the decoder, it gives different attention weights. Maybe it will be giving more attention to the last hidden representation. It depends upon the application also. For example, if you look at machine translation applications, and if it is a machine translation application between, let's say, English language and Hindi or some Indian language. So we know that, okay, the word order is different when it comes to Hindi to or English to Hindi or English to any other language, right? So English follows some word order like subject, uh, verb, object, while Indian languages follow some word order like subject, object, verb, right? So when it comes to this decoding and generating the translated target language sentence, if it is like English to Hindi, then the final few words that you want to generate, okay, the final stage of the decoder will be having more attention on some uh, some hidden representation which is appearing in the middle portion of the source sentence, input sentence, because that corresponds to verb. While if it is like some English to some other language, which is also following the same word order, something like subject, verb, object, then that correspondence for the attention base will be different. Maybe for the last few words of the target sentence, more attention will be on the last few words of the source sentence, or the hidden representation of the last few words of the source sentence. So this attention is basically used for this purpose. I hope you are aware of all this, right? This you may have studied already, right?
So yes, we just one question. So once we get the attention wave, how the dialogue is generated in the basis of that.
Sorry.
Once we get the attention waves, that is alpha T1, alpha T2 for based on the corresponding input segment X phase 3. So how do we generate the corresponding dialogue, meaningful dialogue after it?
Yeah. So here your X1, X2, X3, Xt, they are just different words in the user input. There are different words in the user input, and this attention is over those different words in the user input. You can just think of this attention as that. And now, this is basically the attention mechanism in the encoder decoder frequency. And you often obtain that attention mechanism as some kind of a probability distribution over all these D inputs, so hidden representation of the D inputs. And this probability distribution is obtained using this formula, which is the softmax formula. And you compute each of these scores EAJ as a function of this state at the previous the state. Okay, this is the hidden state associated with the decoder at the previous state, that is ST minus 1. And this score is obtained as a function of that ST minus 1 and each of these hidden representations at J. So the score is going to be a function of both. It basically sees how similar the hidden representation of the decoder is to each of these hidden representations associated with the input encoder, and compute these attention based upon that. Yeah, but the whole process, if you look at, it tries to find some kind of a probability distribution over. When it tries to generate this output YT, it is trying to find out a probability distribution over all possible words in the vocabulary, and then assign a word which is most probable or highest probable. Right? But as we saw in this example, while doing this generation, in these kind of situations, in these specific kind of situations, you don't have to make use of, or you don't have to find out a probability distribution over all possible words in the vocabulary. You only need to find out a probability distribution over whatever input words there are in the vocabulary, and just choose the right input word to output from this set of input words. You don't really have to find out a probability distribution over all words in the vocabulary. So this issue, okay, this issue of the standard or encoder decoder framework trying to model a full probability distribution over all words in the vocabulary. So that is addressed by this pointer net. And the idea of pointer net used is very, very simple and straightforward. What could it be? See, the objective here is that we just want to have a probability distribution over the input words, right? And what do you think, how can we obtain such kind of a probability distribution? But did you understand the motivation behind where we are going?
Yes, sir. But more about the what we have known the attention weights, but the attention can be be having the last word can be having a higher attention weight. So how to form a meaningful response out of it?
Sorry, I didn't get that. What is it?
The attention we are training it as a encoder decoder model, right? We are basically finding out the attention weights here based on as you are showing. So it may happen that the X3 or X4 may be having the higher attention weights. So how we will be forming a meaningful response out of it? Well, because the attention weight may be different order.
See, if you look at this specific example, in this specific example, this is the output I want to generate, right? This is the input, and this is the output I want to generate. So this X1, X2, X3, XT can be seen as something like, hello, my name is Srijit, something like that. And these Y1, Y2, YT, etc. can be seen as this output that you're going to generate. And you can see that, okay, in this particular example, the output that I want to generate here should give very high attention to the first input, first word in the input, and perhaps very low attention to the remaining words. And the second output I want to generate should be such that it should end up giving very high attention to the last word, or the hidden representation has to be the last word, and very low attention to the other words, initial words. So this attention mechanism is going to be helpful in determining, okay, which words I should attend more to generate some particular word at a particular stage.
Yeah, that's so.
Sir, is it going to generate these words one by one? Like as you told that first, it will have higher weight to hello.
Yeah, that is the standard decoder. In the standard decoder that you generally use, you generate them one by one, right? You generate is t minus 1, and you consider its associated state, hidden state st minus 1, and a weighted combination of the input hidden states as input and generate YT, and it generates in a sequential manner.
So for it will generate for all the words one by one. So suppose for my, it will have like very less probability for all. How do we then define what's the less and higher?
It is not doing a translation of this into this into this. It's not like that, right? We just encode everything, all these input words,
Mhm.
get a hidden representation as it with each of them,
Okay.
and then the decoder model considers some DI. DI is nothing but some kind of a weighted combination of the hidden representation associated with the ith stage of the generation, and try to based upon that so we expect the decoder to end up a decoder model where
Sir, they are more natural language.
all
Hello.
in these kind of situations.
So I think your voice is breaking.
To just want to generate fine. Am I audible?
Sir, we lost your voice in between.
Hello. Hello, can you hear me? Hello, can you hear me?
Yes, sir.
Yeah, so when it comes to the standard encoder decoder, this DI that you have formed out of this weighted combination of the hidden representations. So this DI will be used for getting some kind of a probability distribution over all possible words using the softmax function, right? And then you try to predict that word that has the highest probability. But the issue is with standard decoder is that it tries to find out some kind of a probability distribution over all the words in the vocabulary, which is the way they are trained. But we don't have to do that here in these kind of situations. You only want to find out some kind of a probability distribution of the input words because you are only trying to produce as output some of those input words. So how can one do that? So that's the motivation behind the use of pointer nets or introducing pointer net in dialogue systems. And what pointer does is very, very simple. Okay. So what pointer net does is that it finds out the probability of predicting the ith word given the previous words it has predicted and the input user message E. And that probability for predicting the ith word is just alpha I, where alpha is this quantity that you have computed. So if you look at this alpha ij, the attention weights, the way you are computing the attention weights is, okay, you are computing it as a probability distribution over the hidden representations associated with the input. Okay? So if you look at alpha I as a vector, it is a vector over all the different words in the input. If there are some 10 words in the input, it's a probability distribution only over those 10 words. If there are 5 words, it's a probability distribution only over those 5 words. So alpha I, the attention weights on users in order to do this attention weighted decoding. You can just think of those attention weights as some kind of a probability distribution over the inputs, and one can predict what input to be used as output just on the basis of that attention weights alpha I. So this is the idea behind pointer net. It's very simple. Just use attention weights that you have computed as the probability of predicting some word at the ith stage. Is that clear?
Yes, sir.
Any questions here?
Sir, there are more complex problems related to natural language processing, like co-reference resolution or coherence and so on. So how are we tackling these problems with these systems?
See, specifically, no, these systems maintain different modules and it keeps track of information that it has collected over all the past utterances in order to find a response. So if we, as we will see soon, when it comes to some task-oriented conversation system, it maintains some dialogue state tracking, which is a module which is used as a part of dialogue, this task-oriented dialogue system. And this dialogue state tracking, what it does is that it states what's the entity that the user has been talking about. So it maintains that if the user has been talking about this particular domain, like restaurant domain, about this entity, like some particular restaurant or some particular food. So it maintains that in this dialogue state tracking in order to uh, overcome these kind of situations. So even if the user says, okay, that food is good, it will know, okay, what that is referring to because of this dialogue state tracking module, which is present in the dialogue systems.
Okay, sir. Go.
Yeah, but did you understand how the pointer net work and the motivation behind pointer net?
Sir, in this pointer net part, when it says that it directly uses normalized weight alpha I, that part is not little clear to me because there also we are using alpha I, right? In CopyNet also.
You are using alpha I in combining the the hidden representations to that is basically to decide to which hidden representation you should give more attention. And
Yeah,
you form this vector di, which is a
mm,
weighted combination of those hidden representations, and
correct.
use di to generate a probability distribution over all possible words you want to generate.
Yes.
So the probability distribution, the output P of yt that you are trying to predict here, the standard decoder.
Mm.
So this probability distribution over yt is over all possible words. Okay. So it
Oh,
is not only over the input words. So when you look at all possible words, it is nothing but the vocabulary size of the some language that you are dealing with, let's say English, and it's going to be very, very large. And you may not be ending it accurately predicting that, okay, you should end up predicting something like 3G, which is one of the words in the input that the user has provided. Instead, it ends up predicting some very general things. It won't be very accurate. So in certain situation, you know, you can generate more accurately if you restrict your output that you want to predict, the space of that output that you want to predict. If you restrict that only to the set of all words which are present in the input.
okay, yeah, understood, sir. So if it's not that it can predict even those words which are not there in the input, if we are predicting the whole vocabulary distribution on whole vocabulary, right?
Right, right.
Okay, got it.
So, but that's also a drawback with pointer net that it is restricted to predicting only those words which are present in the input. And we will
Oh,
see soon another approach which is known as copy net, which tries to do both, tries to do a generation as well as it tries to do a copying of the input.
okay, sir. Thank you.
Yeah. But as far as our objective, for example, if our objective is only to copy what is there in the input that the user has provided, pointer net is good. And the way it achieves that is by just considering the probability distribution over this yt that it has to predict. That probability distribution is restricted only to those input words. So alpha i's, you can think of this alpha i's that you have here as a probability distribution that you are finding out over the input words. It's basically telling you how much weight that you want to associate with each of these hidden representation. But the way you compute alpha I is you compute it as a probability distribution in the exponential EIJ divided by summation of all inputs exponential of EIQ. So this will result in a probability distribution over the inputs. Alpha is going to be a probability distribution over the inputs, and you can use alpha is to predict your weight. Yes, so this is what this point-to-net model does basically. The point-to-net model conserves this input, and the decoder part of this point-to-net will try to predict some uh, some output, which is nothing but a probability distribution over different inputs or a probability distribution over the position of the input. So, for example, uh, in the first stage, it says that, okay, I will consider the last word in the input. So it predicts something like 4. In the second stage, it considers the second word in the input. So it predicts something like 2. That means if you look at the alpha vector, the alpha vector will be having high probability for 2 and low probability for other words at this stage. The alpha vector with this stage will be having high probability over the first word 1 and low probability over the remaining words. So at this stage, you end up predicting this one. So now, if you look at what is the output that is predicted by the pointer net, it is just a permutation of the input words in different order. Yeah, so this is something like very specific to this particular dialogue systems. You know, this kind of situation may not arrive in general, but in dialogue systems, you may encounter these kind of situations, and pointer net uses specific deep learning models, which is developed for dialogue system. But then, as I just mentioned already, just using a pointer net will be too restrictive that it won't be able to generate words outside the set of words in the input, right? But you want to, of course, generate words which is there outside the word in the input. And to address this, people propose something called CopyNet, which also has this ability to generate words. So what it does is that at each stage of the decoding, so it decides whether to copy a word from the source input that the user has provided or generate a new token which is not in the source. So you can think of the probability distribution over words as a combination of two probability distributions. So the first component of that probability distribution, you can think of this as doing a generation. This generates a new word. And the second component of this probability distribution can be seen as just doing a copy of one of the words in the input sentence. So it contains two components. One component trying to generate a new word, the other component trying to just copy one of the words in the input sentence as the output. Okay? So one can think of this as some kind of a weighted combination of these two component weights being decided at the decoder, and it's going to be different for different stages of the decoder. At some stage of the decoder, you might end up learning that weight to be higher for generator, and it generates a new word. And some stage of the decoder, the weight could be higher for this copy component, and it just copies one of the words in the input as the output. And it makes use of both these components, copy component and the generator component, to generate your file, the response of the system response. The other very other usefulness of this copying mechanism is that many times when you make use of some external knowledge bases, you just want to copy some sentences from that external knowledge bases as it is, without trying to rewrite or trying to generate. So the copying component, which is present in the copynet, can be useful in just copying some of the words from the external knowledge base as it is also. But if you look at this architecture in general, it is going to be something like this. Yeah. So this is the input that you have. Now some user says, oh, hello, my name is Tony Japara, and you expect the system to produce some response like, hi, Tony Japara. Right? So this is what it is trying to produce, hi, Tony Japara. In this case, it just needs to, well, in this case, it is not just doing a copying, because you can see that the first word it has generated, it is something based upon generation. It is not just copying, right? It is just not copying hello as it is there. It is generating something like hi. So it instead of copying, it decided to generate a word something like hi. But the remaining words, the remaining ones are just copy of the input that the user has provided, like Tony Jakara. So in the remaining stages, it decided to copy rather than generate. So it's a mixture of both. It's a mixture model where it tries to uh, mix this generation process and copying process in its decoder. Did you get an idea about this copying?
Yes, sir. And how does it decide like when to copy and when to generate?
Yeah, you can think of this as again some sort of a probability distribution over this generation module and copy module. That probability distribution again learned, just like the way you learn the attention weights, right? Attention weights are going to be different for every decoder stage, right? So similar to that, you can think of having some kind of a probability distribution over this generation and copy that you learn, and decoder decides what to use based upon which one has higher probability.
Okay, sir. And while training like is this trained with this kind of word in which there is a extra word which is not there in the input?
Perhaps, yeah, it depends upon the training data set, and if it has some word which is not present in the input, it learns to generate that.
Okay, thank you, sir.
Sir, so basically it will add the creativity aspect of generation basis on the given training data set only, nothing outside intelligence.
Right, right.
Okay, okay. Thank you.
Right. So these are some specific deep learning models and architectures that have been used in the dialog state tracking. And of course, all these can be, whatever that we have discussed is majorly based upon this LSTM RNN kind of a framework, but all these can be replaced with the transformer-based approaches also. And there are a lot of transformer-based approaches also people use for dialog state tracking. Yeah, but no often,
Sir,
no, yes.
sorry, sir. I just have a question. So in PointerNet, the output that the decoder was generating was the position of the words, right, sir?
Right, right.
Whereas in CopyNet, it is both a combination of generation and the positions. However, the output that the model generates is always going to be tokens. There is no concept of indices here, is it?
Mm, Yeah, it's always some tokenness.
Okay.
Yes. So often many of these dialog systems requires you to generate an output by combining or by considering some external knowledge bases also. And often you may have to come up with models which combines the external knowledge bases and develop deep learning architectures which can consider that external knowledge bases also. Uh, yeah, so this is typical how a knowledge base looks like. Typically, the knowledge bases are in the form of some graphs where different nodes represent different concepts and edges represents connection between these concepts. And to generate a proper response, one may have to traverse through these graphs also and give attention to some specific concepts and relationship and make use of that specific concerns and relationship in making the generation process. I couldn't go through in deep learning models which test this specifically, so I'm not going to discuss about that. But maybe, yeah, there are approaches where they try to combine these knowledge graphs with deep learning models in order to generate these system response. Okay, so what we do now is let's just look at uh, the typical architecture or typical what to say system architecture, not the deep learning architecture, but the system architecture that is followed by these task-oriented dialog system. Okay? So the task-oriented dialog systems, as we just mentioned, they try to solve some specific kind of tasks like booking an accommodation, booking train tickets, booking flight tickets, etc. And in order to be very, very specific, in order to do some specific activity, it has to follow some specific uh, architecture or framework through which it tries to address this. But as the recent works just try to use some end-to-end neural network in order to do that. But if you look at most of the dialog systems for task-oriented applications, they follow a specific uh, framework where different components of the framework try to address different aspects. Okay? Yeah. So this, what you have in the figure is a typical framework that is used by a task-oriented dialog system. So there is a user who will be providing some input in the form of speech or in the form of text. If it is speech, you use some automatic speech recognition to convert it into text. And this is the dialog system. And this dialog system considers this input from the user in the form of text and produces an output in the form of text. Okay? So this is what this dialog system does. The dialog system considers some input from the user, which is in the form of text, and it produces an output to the user, which is in the form of text. Maybe the application might just display that text it has generated or convert that text into speech and provide that speech output to the user. So that's how it basically the interaction might happen. But yeah, if you look at specifically on this task-oriented dialog systems, they generally has let's say 3 components. So the first component is something called natural language understanding unit. Second component is something called dialog manager. The dialog manager itself have 2 components, which is known as dialog state tracking DST and something like this is what is it? Yeah, policy learning component, which is also part of this dialog manager. And often this dialog manager has to interact with some external knowledge base also in order to, okay, in order to generate some actions or generate some response which requires some actions. Now, on the basis of what this dialog manager provides us output, the natural language generator will try to produce a natural language sentence through which we want to uh, communicate with the user. So these are the typical components which is present in a task-oriented dialog systems. And the natural language understanding unit, as the name itself says, what it tries to do is that it tries to understand the user input, the which domain the user input refers to, what is the intent of the user input, and now what are the different named entities, etc., that the user talks about in this specific input that is the user provides to the system. Right? So this is basically the goal of natural language understanding NLU unit. This is the unit here. So for instance, so if the user provides an input sentence like this, recommend a movie at Golden Village tonight. Let us assume this is the input that the user has provided. So, for a dialog system to respond, it has to understand, okay, the user is talking about which domain. Is it some entertainment domain? Is it some, food or restaurant domain? Or is it about some politics, etc.? So it has to understand the domain that the user is talking about so that it can use the appropriate knowledge base while generating a response, right? So one of the tasks in natural language understanding is to understand or detect the domain. For example, here the user is talking about a movie domain. And then you need to understand the intent of the user. Is the intent of the user finding a movie or given a movie finding a theater location, okay, or finding, I don't know, the release date or something? Okay? What is the intent of the user? So the natural language understanding unit have to find out the domain the user is talking about and the intent of the user. For example, this is user want to find some movie which is located at some point at some place called Golden Village at some date like tonight. Yeah, so this is something that the natural language understanding unit has to do. Apart from just understanding the domain and intent, it also have to understand some minute details which is present in the input sentence, like the location he is talking about or the date he is talking about. So, for example, from this sentence, it can understand the location is going to be something like Golden Village, and the date is going to be something like tonight. But it has to understand that. So, this this ability to understand the location, time, etc., from a given sentence can be seen as something similar to named entity recognition, where we try to find out the named entities in a given sentence. And some techniques similar to named entity recognition can be used here also. For example, now have you heard of this IOB tagging scheme? Where IOB represents inside, outside, beginning. So, something like an IOB tagging scheme, it has to use to identify the location, time, etc., that the user is referring to within a given user input. So, for example, it has to produce some output like this, where it marks each word in the user input as outside some named entity, or it's the beginning of the named entity, or inside a named entity, or a beginning of another kind of named entity, etc. So it has to do this, and this is often known as slot filling because there is this component dialog state tracker which maintains some predefined set of slots like location, uh, type of the movie, genre of the genre of movie, then date, etc. Okay, these are the different slots that the dialog state tracker maintains, and at every turn on the base of every user utterance, now this NL you have to point out, okay, what kind of slots the user is talking about, and on the basis of that, it has to fill the slots that the DST is maintaining, dialog state tracker is maintaining. So once the dialog state tracker feels that it has enough information to query some database to generate some action like booking a movie ticket or booking a hotel accommodation, then it can do that, right? Based upon whatever it has information it has collected so far. Yeah, but specifically, this is the objective of natural language understanding component, NLP component. Yeah. When it comes to dialog state tracking, it maintains all the some kind of something like a summary of all the information it has seen so far, which is provided to it by the NLP unit. Okay, so the dialog policy learning module, it decides what action this dialog manager has to take based upon the information it has gathered so far. Whether you should ask for some more information, some specific information which is not which has not been collected so far. For example, the user has been seeing that he want to see this movie at this location, but the user never mentioned about the date, right? Without having the date, one cannot book a movie ticket. So the policy learning module decides that okay, the user didn't provide the date so forth, so it will decide I will ask okay which date the user want to see the movie. Okay. So the policy learning module decides all these what action to take, what to ask the user next, so that it can complete all the information it requires to do a movie booking.
Sir, one query.
Yeah.
Sir, in DST, is this similar to what CopyNet was doing in terms of adding additional words which is not in input?
You can think of something like that.
Okay.
Well, actually, people use CopyNet to model DST, their state tracking. At every stage, you decide to keep some of the information it has previously gathered, and you try to add few information from the user input, which it didn't have before. So, so it may not be that the DST has always needs to be modeled using CopyNet, but when it comes to neural network models to model DST, people often use CopyNet kind of models.
Okay, thanks.
Yeah, that's another motivation for CopyNet. Like, you can model these kind of dialog state tracking, etc., using CopyNet models. Yeah. So now, once the policy learner module decides what information needs to be gathered from the user, then the natural language generation module uh, tries to generate a sentence through which it tries to infer or gather that information from the user. If you look at this particular example, the user said that recommend a restaurant at Chinatown. So natural language understanding unit has understood that, okay, the user is talking about some domain like a restaurant. The user is talking about some particular location like Chinatown. So it feeds that into the DST module, and the DST module fills whatever source that is needed for booking a restaurant based upon the information of its offer. But it finds that, okay, the user didn't provide any information about the number of people for whom the restaurant needs to be booked, right? The table needs to be assigned. So the policy learning decides, okay, it has to request uh, the user to provide the number of people. So on the basis of that, the natural language generation unit generates this sentence like, how many people do you have? And the user responds saying, okay, this many people, etc. And you keep conversing with user until you get enough information to make a booking. So this is fundamentally what the task-oriented dialogue systems does. To to look at let us look at slightly more into these each of these components. As already mentioned, the natural language understanding unit has three main jobs. One is domain classification, like here you find out, okay, this is a domain about movie. Then intent detection, okay, find what the intent of the user is. Is it about finding out the movie or finding out the location of a particular movie, etc. Then no, it also find out all these named entities that the user talked about in his input, right? So, but if you look at the domain classification interpretations, they can be seen as simple classification problems, and one can use classification models like the neural network classification models or any deep learning classification model to perform domain classification and intent detection. But if you look at this slot filling, where you need to fill different slots that the DST is maintaining, like the location, date, movie name, etc., etc. No, that is treated as a tagging problem, just like named entity recognition or part of speech tagging. You need to tag every word in the sentence as something which can be useful to fill the slot or not useful to fill the slot. So all these O that here represents, okay, there's something which is not useful to fill the slot, but all these B destination, I destination, B time, etc. refers something to the words which can be useful to fill the slot. And that can be seen as solving the standard sequence labeling task. So these are some algorithms for sequence labeling, right? These are these marker model algorithms, CRF algorithms, and sequencing, as in using some sequence to sequence models or in HMM, etc., whatever. So it maps the user to some output, which is sequence of tags like this. So finding out the intent domain, etc., is very difficult, or because often the user talks very short sentences when it comes to dialogue systems. And out of that short sentences, finding out the domain, intent, etc., is difficult. So often these domain classification methods, intent detection methods, etc., they maintain a history of utterances from the user. And on the basis of that, they try to predict the domain and intent of the user. So this is basically the natural language understanding unit and the techniques one have to use under the natural language understanding unit. Yeah. In some works, they try to predict simultaneously all the three tasks associated with NLP, like domain classification, intent detection, slot filling. They try to predict all of them together as a multitask learning problem, so that now they can probably share some knowledge across each other in solving the task. Now, coming to dialog state tracking. So as I mentioned, the dialog state tracker basically maintain some predefined set of slots depending upon the domain. For different domains, the slots it maintains is going to be different. And as you see, every utterance from the user, like every term, it tries to make use of whatever NLU module has found in order to fill this predefined slots. Okay. So NLE module does this classification of the user messages, and the DST module tries to find out the slot value for each slot name in the pre-existing slot based upon the domain they are talking about. For example, if it is something like a restaurant or maybe like movie domain, you maintain something like intent slot. Okay, what is the intent of the user? Book a movie or something. Then the domain slot, what's the domain he is talking about? Name slot, name of the movie or name of the restaurant, etc. Then the price range slot, is he talking about cheap restaurant or very costly restaurant? Then genre slot, very useful for movies, like what genre of movies he's talking about. Then the destination slot, where he wants to go to book a restaurant or watch movie. And the date slot, where to which date you want to book a movie or table. So all these are some sort of a predefined slots, which is user-defined slots many times, that this DST, data state tracking, is maintaining. At every terms, the NLU provides some information to the DST to fill these slots. So when it encounters some user inputs like this, recommend a movie at Golden Village tonight. On the basis of that, it will fill some of the slots. Like it fills this slot domain as movie. The name, okay, he didn't provide any name, so name is none. Price range is not provided, so it remains as none. Genre is not provided, so none. Destination is provided, so it becomes Golden Village. Date is provided as today. So now on the basis of what information is present in the DST, then the next module can decide to book a movie or restaurant or ask users some queries to further fill the slots at DST. So the NLP module tries to tag the user message, but the DST module tries to find out the values from the user message to fill that the existing form. Yeah, and this output of the NLP module is taken as input to the DST module. And this is one typical example of what's happening if you compare the NLU, dialog state tracking, etc. Okay. So let's assume that the system asked this question, which are part of the town, and the user responded like something like north area. So based upon this user response, the SLU finds out that okay, it has received some particular information about the location and provide this information about the location area north to the dialog state tracker, and the dialog state tracker then updates the slot information with something like area being north and other informations perhaps may not have from this based upon the user message. So if the user message is something like this, okay, a cheap place in north. So in this case, the NLU finds that okay, the user not only just provides the area information, but it's also providing the price range, which is cheap. So it can fill not only the area information, but also price range also based upon what the user has provided as input. So both the slots gets filled based upon this user input. Yeah, so this is what basically is happening in the dialog state tracking, that you keep on maintaining or keep on filling this slot information at every turn as you get more and more information from the user. And also, you make use of this DST, whatever present in the DST, in order to decide what to ask the user also. And that is taken care of by this policy learning module. And what this policy learning module, what it does is that it considers the dialog state that is maintained by DST, and there could be possible actions, maybe a request for place, request for date, or query a database, etc. And this module, based upon whatever dialog state is maintained by the DST, predicts some actions to take or decides what action to be taken. So it is a mapping from the dialog state to some action, which is then fed to the natural language generation module. So far what we have discussed, is it clear? Any questions?
Sir, in here there is like some correct and right thing. Is it like when the next slot gets updated, it marks the previous one as wrong, or what is this sign here?
So I think this is some kind of a information which is present in the, this is labeling. Okay, this is so often you train this gyro state tracker. Many times you use a natural, neural network to decide what slot to be filled, etc., or any machine learning model. And these are the, this you can see these as some kind of classification labels the user has provided or you have obtained from data set in order to train a learning algorithm which tries to do this dialog state tracking.
Okay, so, what is this SLU number 0.2, 0.1, this thing?
These are the probabilities with which the dialog state tracker is predicting. So it predicts
So
some.
it's
Okay, so there are different possibilities it want to predict. Okay, so it might end up one prediction. Okay, there's a probability distribution over possible predictions by the dialog state tracker. So it might predict that, okay, this user input is about some North African food with some probability 0.2. This user input is about some area north with probability 0.1. And I don't know, nothing with probability 0.7. Now these are the different, for in this example specifically, because this data state tracker is not predicting correctly. But in this case, you can see that the dialog state tracker is predicting that this user input is about area north and price range cheap with some probability 0.7, and area north and food North African with probability 0.1. I don't know, like none with probability 0.2. So these are, you can think of this as some kind of a probability distribution over possible outputs that dialog state tracker is predicting.
okay, sir. And that PL, is that is it reinforcement based model?
PL can be supervised learning module or reinforcement learning module. And many times people use a reinforcement learning module to train PL because of the nature of PL. It has to take some action based upon the environment, and that is very similar to a reinforcement learning setup. And people often use a reinforcement learning algorithm to train PL module.
Okay, sir. Thank you.
So people use deep learning models in the DST track, and many times these deep learning models make use of a lot of features, I don't know, like some SGO score, rank score, Rafield score, etc. as input in your network and predict the probability of each slot value pair. And this is what it is. There is the probability of each slot value pair that the deep learning model for DST is predicting based upon the input from the NLU, natural language understanding module. But there are approaches where people don't try to predict some specific or fill some specific predefined slot value, but it tries to just try to uh, predict some values or generate some values on slot name based upon the user input using A3 planning methods. But those are the different approaches that people follow data state. Now, coming to policy learning, the major, the main objective of the policy learner is to predict the action based upon the current state of the dialog state track, based upon whatever the slots that has been filled so far. It has to predict some action. The action could be something like request user for some more information, some specific information about some slot which is not at field, or query some database and get some information from the database. So actions could be all these, but the policy learning module decide what action to take based upon the state of the dialog state tracker. Yeah, so to train such kind of a policy learner, people use supervised learning technique as well as reinforcement learning technique. Yeah, supervised models require some quality training data to predict the actions correctly. But most of the approaches for policy learning is based upon reinforcement learning because it is natural, the natural way to model things. You are given some state in the form of dialog state tracker and you want to decide an action to take, right? So that's the natural way the reinforcement learning works, and many of these policy learning is based upon reinforcement learning. And there are different approaches people came up with in policy learning, something called multi-agent dialogue policy learning, where they have multiple agents interacting with each other, performing or imitating as a user and an agent and learning the policy simultaneously on that. Yeah. So the natural language generation, okay. So at the initial stages of natural language generation, people treated that also as a specific pipeline where they take input from the policy learning. The policy learner will provide what action to take and convert that action to take into a natural language sentence. And that is what this natural language generation unit does. So if the action that is suggested by the policy learner is just to inform the user about some movie named Wonder Woman at this Golden Village. So the action module, policy learning module, will provide an output something like inform, name Wonder Woman, genre, action, destination Golden Village. So from this, it has to generate some sentence like there's an action movie named Wonder Woman at Golden Village. So, earlier approaches to natural language generation followed some specific pipeline-based approaches where they determine what to say, which is something very domain dependent, and then based upon that, try to generate how to generate a sentence, doing some sentence planning, etc. But all these days, people just use a deep learning algorithm, an end-to-end deep learning algorithm to generate the natural language output based upon this whatever information that the PL module provides you. So this is just some simple sequence to sequence model or any encoder decoder model that people use in deep learning that can be used directly in this natural language generation state, where one considers this as the input and produce this output by just generating this natural language symbols. So apart from all these approaches that we have discussed, in dialogue based task-oriented dialogue systems, also people have come up with some end-to-end deep learning methods, right? End-to-end deep learning methods for task-oriented dialogue systems. So the model-based approaches are very good. They provide very precise answers through which one can interact with the user. But however, they are very, very limited. So you need to come up with handcrafted slots for every domain. So as you want to develop a system for every new domain, you want to come up with some handcrafted slots, etc., for each of those different domains. And you cannot do all these transfer learning kind of things, transferring the knowledge that you have gathered in one domain to another domain, etc., when you go for these module-based approach. So another option is that you can make each of these modules differentiable, right? So generally, people develop each of these modules as a independent component. There's no end-to-end train. Each of these modules are trained to accurately predict what task they are supposed to predict. But eventually what happens is that you have to make use of each of these modules in a sequential manner, one after the other, to produce your final output. And the final output will be having some error, which is not propagated back across all these different modules. And these modules are trained independently. So that may not be very, very helpful, like to improve the accuracy of predictions when you want to predict for some relatively new domain. And one way is that all these modules parameterized as a function of some neural network, and try to do backpropagation and learn the parameters of this neural network model, each of these modules in an end-to-end mode. So there are some recently all these different modules are being modeled using some deep learning models, and one of the major issues is how to combine let's say knowledge bases and whatever information that you have collected so far in the dialogue state tracking in order to generate this action, what action to take, and how to model that using a deep learning architecture. And that's where these knowledge base integrated deep learning models comes into picture. Yeah, so one can even use, instead of a explicit knowledge base and querying the knowledge base, that whole part can be replaced by large language models, which already have a lot of information, right? It has a lot of information knowledge base. It may not be up to date. Often you may need to provide some up-to-date information about movies, restaurants, etc. So, but one potential way is to replace that knowledge bases with LLMs, which has a lot of knowledge already in them, and use this as a part of this whole dialogue system. Yeah, so this is the overview of majorly this task-oriented dialogue system. And open domain dialogue systems are often always trained as end-to-end manner using encoder decoder deep learning models on huge amount of training corpus, the way the LLMs are trained. So as far as the evaluation is concerned, you can use the standard evaluation metrics like BLUE, CDAR, etc. And there are some tasks, as we can see, are classification tasks, like finding out the intent of the user, domain classification is the classification task, and you can use these accuracy, F score, etc. in the case of classification tasks in dialog state tracking in dialog systems. Right. So this is one of the very good reference that you can follow to understand the recent advances which is happening in dialog system, especially from the deep learning perspective. So I will stop here, and if there is some questions on what we discussed so far, we can discuss.
So this energy is similar to the encoder decoder architecture for machine translation, right? Or it is only
Right.
decoder only block?
You can have a encoder decoder architecture, or maybe like the decoder only architecture. That's people try
Okay.
different approaches.
Sir, can you please explain that part where you told that we can replace this knowledge base with LLM? Because in LLM itself, we use some of the knowledge base, right?
Yeah, yeah. This part, right? So this is, people have something that people have tried, like, instead of querying a knowledge base, and because one of the issues is how do you integrate this knowledge base into a deep learning framework so that we can have uh, this module, the whole module, the dialog manager module, it can be modeled in a neural network, can be modeled using a neural network. So that part has been bit difficult, and people one can think of replacing the whole thing using an LLM which already has some domain knowledge. But the issue is that LLMs are not updated with the latest information, right? So yeah, LLM itself have to depend upon some external knowledge base to get a very accurate information. Maybe one has to combine LLM with the RAG in order to accurately obtain some information. Because if you are referring for some movie which is happening, which is being playing in somewhere in Hyderabad or something, you need to have some latest information about that, right? Which
Yeah.
It's not really possible with an LLM, but it also needs to be combined with some knowledge base to produce that accurate information.
Okay, got it, sir. One more question, right? When we make this end-to-end things, in that, how do we take this PL part, which is reinforcement learning?
See, there are approaches people have used, like deep Q learning, deep reinforcement learning framework, right? One can say just think of using that similar kind of an architecture there, where the actions are predicted using two values, etc., are predicted using some deep learning model.
Okay, and this loss will flow from a start to till the first stage through all the models?
Yes, yes. That is ideally one wanted to achieve, and that is what is expected to do when you try to parameterize each of these model using some neural network, or when you develop some end-to-end deep learning based approaches.
Okay, sir. Thank you.
Sir, I have a question on the policy learning part. So be it supervised setting or the RL-based setting, as far as I understand, we need to define the action set beforehand. And among these action set, one action is chosen and is provided as input to the natural language generation portion, right? So are these so because natural language generation is also kind of a text-to-text model, are these actions also in textual format? So what exactly
So
is
the
the output
actions,
of the
so
policy?
for
Yeah.
example, if you look at here in this example, so if you look at this example, so this is the output from PL part. and the action is inform. The action is to basically what it means is that okay, you just inform the user. Okay, there is a movie named Wonder Woman uh, playing at the Golden Village. So based upon this input that the PL module provides to the natural language generator, the natural language generator has to generate these natural language sentence like there is an action movie named Wonder Woman at Golden Village. So sometimes the PL module can generate some different kind of actions. For example, if you look at this example, in this example, what the PL module has generated is some action like request NumPy. So here the action is request. So where it is asking this NLG to ask the user to provide some information about NumPy. So the action is request rather than inform, and therefore the NLG is generating a sentence like how many people do you have? Yeah, so it's basically represented using different words, whether it is a request, information, etc.
Sure, sir. Got it. Thank you.
Okay, so yeah, you can follow this reference. It's a very nice reference to understand the latest trends in dialog system. And yeah, so then if there are no questions, people. So have you booked for coming to campus next week?
Yes.
Sure. So this exam schedule is given to you, right? At least as I know, we'll be having NLP exam on Saturday afternoon, correct?
Yes, sir. Monin sir said somewhere 2 hours between 1:30 to 4 p.m.
Sure. And if you are taking this content computing, so that exam will be on Saturday morning. And if any of you are taking Bayesian data analysis, that exam will be on Sunday morning.
Yes, sir. Sir, are there any further classes for NLP and BDA now?
No, there are no further classes on NLP and BDA.
Sir, at what time are the morning exams going to start, sir, generally? Because for people who are locally there in Hyderabad.
Around 10 o'clock. You can expect to start around 10 o'clock.
Sure, sir. Thank you.
Sir, BDA presentations would start at what time, sir?
So what do you think? Is it fine to have it on Sunday after exam?
Yes.
That is fine, right?
Sir, how long will it be?
The other option is that we need to keep it on the weekdays in the evenings. Like
Sir,
you
I
can
think
have both also on
yeah,
Sunday after the exam as well as on the weekdays in the evenings.
Sir, can we have them after the exam, sir?
Can we have them after the exams?
Because it will be hard for you to prepare for the exam and for the presentation, right? So I'll
Yeah.
do one thing. I will just keep some floats, and you can decide as per your convenience. I will add some slots to uh, that Excel sheet that I shared, and you may choose based upon what is convenient.
Sure, sir. Thank you.
Sure, sir.
All right. All right, then see you all next week.
Sir, just one request. Can you upload the PPT that you are teaching on?
Sure, I'll upload that.
Thank you.
Sir, sir, one question, sir. Sir, can we like can fine tuning of LLMs replace all these steps of NLU, DST, policy learning, and natural generation, language generation?
I think to some extent it can, especially if you fine tune and maybe add these retrieval augmentation, augmented generation, everything. It can to some extent it can be helpful, but still, uh, it, it, it is more useful for open domain dialogue systems where you just want to have some general chit chat with the user on some specific domain or some in general with the user. But now when it comes to task oriented dialogue system, you have to solve some specific task, right? You have to do some specific action like booking some restaurants, etc. So that requires some additional component and additional work in addition to what just a generic LLM can provide.
Right, sir.
Okay, see you all then. This weekend, this weekend is already over, right? Have a good day.
Thank you, sir.
Thank you, sir.
Thank you, sir. Good
Thank
day.
you, sir.
Thank
Thank you, sir.